In this lesson, we're going to learn how to integrate a whole bunch of different combinations of products of trig functions. And we're doing this because in the next section, we're going to learn a method called trig substitution. And within that method, we're going to be using some of these methods as well. So it's going to build up into the next section. So the main idea of this lesson is to learn how to integrate the combinations of the products of powers of sine x and cosine x and other trig functions by rewriting these expressions using trig identities or just rearranging the powers of the expression. And then that way, once we rearrange that or use identities to rewrite the expressions, the goal is to then be able to use substitution or integration by parts. And so these can get kind of complicated, and so can the ones in the next section. I highly recommend that you have your reference sheet in front of you that I posted in the first module that has all of our formulas and things in it, because some of these formulas you may not have used in a while, like the double angle formulas and things like that you're going to have to go back and look up. So keep that handy as you are working through these examples. So we're going to start off with a nice, easy example, and then we're going to work up to the harder ones, and we have a set of steps or guidelines that you can use to do these, which we'll get into a little bit later when we do some of the harder ones. Right now, I just want to start off with some of the easy ones. So keep in mind, as you're doing this, the whole point is to rewrite the integral in some way that we can use substitution or integration by parts. So this first example is super easy. We have the integral of cosine to the third x sine dx. We're going to let u be cosine x, so that way when I take the derivative of u, I get minus sine x dx. I can replace cosine with u, so I would have u to the third. I can replace sine x dx with negative du. And so now I can use the power rule for integration, and I get negative u to the fourth divided by 4 plus our constant. And then when I go back and substitute in so that we have everything in terms of x, our final answer is going to be minus cosine to the fourth x over 4 plus c. In this next example, we're going to evaluate cosine squared times sine cubed. Now, notice up here, that is generalizing it, where j is the exponent for cosine and k is the exponent for sine. So notice in this case, k is 3, so k is going to be odd, and we're working you up to recognizing this. When we look later on at the guidelines, this is going to help us determine which of those guidelines to use. So for this example, the first thing we're going to do is split the sine cubed up into sine squared times sine. So that goes right here. I just bring down the cosine squared. Now we're going to use a Pythagorean identity from trig to substitute for sine squared x. So I'm going to substitute 1 minus cosine squared in for this sine squared x. So that goes here. I bring down the sine, bring down the cosine squared. And now if I let u be cosine, du is going to be minus sine dx, and I can use this and do a u substitution that works out very nicely. So if u is cosine, then this is going to be u squared, 1 minus u squared, and then the sine x dx is going to get replaced with the negative du. So here's my negative, here's my du. Now I can expand this, so I get u squared minus u to the fourth du. Now this is much easier to evaluate. So I have, oops, I noticed I forgot my minus here. Let me write that in here. Right here. Okay. All right, so that gives me, when I evaluate this, I get minus u to the third over 3 plus u to the 5th over 5, and that becomes a plus because I have a double negative, and then plus my constant. And then I go back and resubstitute in terms of x, so I have minus cosine to the 3rd over 3 plus cosine to the 5th over 5 plus c as my final answer. Now for this example, we're going to evaluate the integral of sine squared x dx. We are going to have to go back for this one and recall a double angle formula for cosine, and we're going to rearrange it for sine squared. So we're going to substitute this in for sine squared. So I'm going to rewrite the integral of sine squared x dx as the integral of 1/2 minus 1/2 cosine 2x dx. Now this from here makes it much easier to integrate. So when I integrate 1/2, that gives me 1/2 x. When I integrate 1/2 cosine 2x, that's going to be minus sine 2x with the 1/2 in front here that we brought down. But then using the chain rule in reverse, we have to divide by the derivative of that inner function, which is 2. And then, of course, we have our plus constant. And then when I clean it up a little bit, I get 1/2 x minus this 1/2 divided by 2 becomes 1/4 sine 2x plus our constant. So here is our final answer. Now, looking at the problem-solving strategy for integrating products of powers of sine x and cosine x. So here's the general format that we're looking at. K is the power for sine and J is the power for cosine. Okay, so we're going to use these guidelines to help us understand what to do, because there are so many different options out there. Okay, we're going to integrate cosine to the 8th times sine to the 5th. So in this case, 8 is our J and 5 is our K. So we're looking for when J is even and K is odd. All right, so that would be this first method right here. So we're going to rewrite sine by writing it as 1 less power times sine x. So that's what we're going to do here. We're going to rewrite sine to the 5th is equal to sine to the 4th times sine. See, we're writing it so that it's 1 less power times sine, so that when I multiply this out, I still get sine to the 5th. And then it says, use your Pythagorean identity to rewrite that sine that's to the even power in terms of cosine. And then when you integrate, you can let u be cosine x. All right, so we have cosine 8x sine to the 4th times sine x. We rewrote that. That was sine to the 5th. And then we're going to rewrite sine to the 4th as sine squared squared. And when I replace the sine squared with 1 minus cosine squared, I get 1 minus cosine squared squared. So this is still equivalent to sine to the 4th. I'm bringing everything else down. Now I can use substitution, let u equals cosine x, so du is going to be negative sine x dx. So anywhere I see cosine, I'm going to replace it with u. So I have u to the 8th. This is going to be 1 minus u squared, the whole quantity squared, times, and then sine x dx is going to get replaced with the negative du. So here's my negative, here's the du. Now I can just use some algebra to expand this. I'll let you guys do that on your own. I know you know how to do that. You square this, and then you multiply it by u to the 8th, and what you're going to get is u to the 8th minus 2u to the 10th plus u to the 12th. I still have to remember to bring that negative down in front. And now this makes it much easier to integrate. So this is going to be negative u to the 9th over 9 when I integrate this. This negative and this negative is going to make a positive. So I'm going to have 2u to the 11th over 11. Then I have minus u to the 13 over 13 plus our constant. And then I go back in and substitute for u. U is going to be cosine. And then this will be our final answer. In this example, we're going to evaluate the integral of sine to the 4th x dx. When we look at our general statement here, j is our exponent for cosine and k is our exponent for sine. So if you notice, j is going to be 0 in this case and k is going to be 4. Since they're both even, when you go back up and look at those guidelines I gave you in the previous page, option number 3 says if both j and k are even, and then it gives you some identities to use for double angle. And if you can't remember these, go back and look at your reference sheet. This one was rearranged for sine squared, and this one was rearranged for cosine squared. And so we're going to use these formulas here to substitute so that we can evaluate this integral easier. So I'm going to rewrite sine to the 4th as sine squared squared. And that way I can replace the inner sine squared with 1/2 minus 1/2 cosine 2x. I'm replacing it with this. And then when I square this, I get 1/4 minus 1/2 cosine 2x plus 1/4 cosine 2x dx. And then I can use this to replace cosine squared. This here with this here. The rest of it is just going to get copied down. So this is replaced with this. Now I'm going to clean this up again. Everything just gets carried down here. When I expand and multiply through by the 1/4, I get 1/8 plus 1/8 cosine 4x. And now I can find the integral of this a little bit easier. So I'm going to get 1/4 x minus sine 2x over 4. The sine 2x over 4 is coming from this 1/2 and then dividing by the derivative of the inner function, which is 2. And then I get 1/8 x. So when I combine the 1/4 x and the 1/8 x, I get the 3x, or the 3 over 8x. And then when I integrate this, I get 1 over 8 cosine 4x, but then I have to divide by the derivative of the inner function, which is where this 32 comes from. I have 8 in the denominator, and then I have to divide by 4, which gives me a 32 in the denominator. So this is our final answer. Now for this next rule here, really we're just kind of going back and reviewing some old trig identities. These I do not believe are on your reference sheet, so you may want to add these to your reference sheet if you want everything together in one spot. But basically these are just your product to sum formulas that we talked about in trig, and we can use these for substitutions for your integrals to set them up in a way that makes it easier to evaluate. So in this example here, we have sine of 5x, cosine of 3x. So we're looking for a product of sine and cosine. So here's sine and sine, here's cosine and cosine. Here's sine with cosine here, it's the second one. So we're going to use this as a substitution. Now our A in this case is 5 and our B in this case is 3. So I labeled it here so it's clear and easy to read. So we're going to use this substitution right here. So I'm going to substitute sine 5x cosine 3x with this right here. So I have 1/2 sine, and then I'm going to take A minus B, so that's going to be 2x, plus 1/2 sine, and then I'm going to do A plus bx. A plus bx is 8x. So now I can evaluate this directly. When I integrate 1/2 sine 2x, I'm going to get negative cosine 2x divided by 2, and when I multiply that by 1/2, I get 4 in the denominator. When I integrate 1/2 sine 8x, I'm going to get cosine 8x with this is going to be a minus actually, a minus cosine 8x. And I have to divide by the derivative of the inner function, which is 8. And when I multiply it by the 1/2, the 2 times the 8 in the denominator becomes 16. And then, of course, I have my plus c. So this will be my final answer. So you have these trig identities here that you can use as well. Now, when we're dealing with integrating products of tangent and secant, we're going to have similar tactics where we're going to use identities and rearrange the expression somehow so that we can do a U substitution or even an integrated by parts method. And so before we get started, just a quick reminder of some of the integrals that we should already be familiar with. Okay, so keep this as a reference. These are on your reference sheet, by the way. And we're going to start off with a nice easy one, and then we're going to build up to some harder ones where we use the guidelines again. So in this example, we have secant to the 5th x tangent x. Here's our general format. Okay, so we have secant to the 5th tangent x. I'm going to rewrite secant as secant to the 4th times secant times tangent. So this is still secant to the 5th. I just split it up. And now I can let u be secant x. So when I take the derivative, I get secant x tan x dx. So I'm going to replace secant x tan dx. I forgot my dx here. But when I replace this with my secant x tan x dx, I can replace it with du. So this all gets replaced with du. And then this just becomes u to the 4th. So when I integrate, it's really, really easy. I just take the integral of u to the 4th is u to the 5th over 5 plus my constant, and then I resubstitute in terms of x. So just like before, when we were doing products of sine and cosine, there's some strategies we can use. And they're identifying k and j as the powers of tangent and secant, respectively. So we're going to look at those powers to help us determine which method to use. In this example here, we have the integral of tangent to the 6th, secant to the 4th. So because both our k and our j are even, we're going to use method 1. And when we use method 1, we're going to break up secant so that it's secant squared, so then I can substitute our identity that secant squared x is equal to tan squared x plus 1. So this secant to the 4th, I'm going to rewrite as secant squared times secant squared. And then I'm going to substitute secant squared with tangent squared x plus 1. Now, according to this method 1, then we're going to let u be tan x. So when I take the derivative, I get secant squared x dx. And so I'm going to replace the secant squared dx with du. So this now becomes du. This becomes u to the 6th times u squared plus 1. I can expand that to u to the 8th plus u to the 6th, and then when I integrate, I get u to the 9th over 9 plus u to the 7th over 7 plus my constant, and then I resubstitute so that it's in terms of x. Now, in this method here, we have tangent to the 5th, secant to the 3rd, so both of my exponents are odd. So we're going to use method 2 here. Method 2 tells us to break tangent to the 5th down into tangent to the 4th times tangent. And then I can rewrite tangent to the 4th as tangent squared squared. So this is still tangent to the 4th times tangent, which is tangent to the 5th. And then I can use this tangent squared identity. This is one of our Pythagorean identities. Solve for tangent squared. And I'm going to substitute this secant squared x in here. So I have secant squared x minus 1 squared. And then all of this I'm going to carry back down. Now, according to the method, we're going to let u be secant x. So when I take the derivative of u, I get secant x tan x. So secant tan dx is going to be replaced with du. So that's this and this that's going to get replaced with du. So now I'm left with secant squared x minus 1 squared times secant squared. And since we let u be secant, that's going to be u squared minus 1, the whole quantity squared, times u squared. And then this and this is my du that's right here. Now, when I multiply that out, I get u to the 6th minus 2u to the 4th plus u squared. And then I can take the antiderivative and I get u to the 7th divided by 7 minus 2u to the 5th divided by 5 plus u to the 3rd divided by 3 plus our constant. And then we go back in and substitute in terms of x. In the next example, we have evaluate the integral of tangent to the 3rd x dx. In this case, our j is 0 and our k is 3. And if you look at the guidelines, that would be using method 3. So when you use method 3, it tells you to break up the tangent, take the power down by 1, and then multiply by tangent. So we have tangent x times tangent squared. And then we're going to use a Pythagorean identity to make a substitution that tangent squared is equal to secant squared minus 1. Then it goes on to tell us to multiply this through and then split it into two integrals. So when you distribute this tangent x and you break it up into two separate integrals, you get tangent x secant squared x dx minus the integral of tangent x dx. This one we can evaluate directly using the formulas at the beginning of this topic that was given. And then for this one, we can use u substitution and let u be tan x. So when we take the derivative of u, we get secant squared x dx. So this here, secant squared x dx, can be replaced with du. And then tan x can be replaced with u. And then, so this one we can evaluate directly from those formulas. And then this one is u squared over 2. And then we have to, of course, go back in and resubstitute tangent for u so that we have everything in terms of x. So this is going to be our final answer. This integration question here, integrating secant to the 3rd x, I would take note of this because we're going to use this again in the next section. And rather than have to go through all these steps again, if you make note what the answer is, you won't have to go through all these steps again. It will save you some work. So make note of what the integral of secant cubed is at the end. Because our value of k is even, k is our power for tangent, which in this case is 0, and j is odd, which in this case j is 3, so that's odd, we should use method 4. Now method 4 tells us to use integration by parts and to use the Pythagorean theorem, tangent squared is equal to secant squared x minus 1, to use that as a substitution. So to start off, we're going to use integration by parts. And we're going to let u be secant x. And when we take the derivative of u, we get secant x tangent x dx. We're going to let our dv be equal to secant squared x. When we work backwards to find v, we get tangent x. Now that we have what we need for integration by parts, we have our u, which is secant, times our v, which is tangent, minus the integral of v, which is tangent, times du, which is secant times tangent dx. So if I take the tangent x times this tangent x, that gives me tangent squared. Substitute secant squared x minus 1 for tangent squared. So I put that in there, and I still have this secant left that I bring down here. Everything else is just carried down. Now, when I distribute this, I get secant to the third x dx plus, so I'm going to distribute this and break it into two integrals, and that will give me a plus secant x dx. This minus, and this secant multiply to give me the secant x. So if you notice, we have the same thing here that we started with. So when we did this in the last section, when we did integration by parts and we ended up with the same thing we started with, we try to isolate that and then divide by the coefficient in front to get our answer. So what we're going to do is I'm going to take this and add it to both sides. So this here and this here are like terms. I'm going to add this to both sides, and I get two integrals of secant cubed x. This comes down, and when I integrate this directly using our formulas at the beginning of this portion of the lesson, I get the natural log of secant x plus tan x, and that I just bring down. So really the only thing I did from this step to this step is directly integrate that secant x dx, and I added secant cubed to both sides. Now I have two integrals of secant cubed, so I'm going to divide both sides by 2 and get this, and then add in my plus c, of course. All right, the last topic in this section, we're going to talk about the reduction formulas, and these are formulas that you may or may not have on your reference sheet. I honestly can't remember if they are on your reference sheet, so you might want to check, and if they're not there, add that in. So these are going to help us rewrite integrals in a different way so that we can integrate it easier. So we're going to make some substitutions here. Notice this next example here is the example we just did up above. But now we're going to use this integral, and we're going to apply the reduction formulas and see this integration done in a different way. So this is secant to the third. So we're going to use this first formula right here, and n is going to be 3. So since n is 3, we are going to rewrite anywhere that we see an n, we're going to put in a 3, and then make all of our substitutions. So this is going to be 1 over 2, so that's this 1/2. Secant to the 3 minus 2 is secant to the first, times tangent x, plus 3 minus 2 is 1, n minus 1 is 2, so we're going to have 1/2. And then this is going to be the integral of secant to the first dx. Now, by reducing the power, by using the substitution, we have 1/2 secant x tan x plus, and then we have this integral here that we can use our direct integration formula for. So when I take and evaluate 1/2 the integral of secant x dx, I get 1/2 the natural log of secant x plus tan x, and then of course my plus constant. All right, now in this next one, we're going to use the reduction formula for tan 4. So that's going to be, if I scroll back up, we are going to be using this formula right here. All right, so in this case, n is going to be 4. So when I use the formula, I'm going to get 1/3 tan to the third x minus the integral of tan squared x dx. I still don't have this reduced to an integral that I can directly integrate, so I'm going to apply the reduction formula again with n is equal to 2. So this is going to get carried down. I'm going to have minus, and then inside here is going to be this integral with the reduction formula applied again. So when I apply the reduction formula again, I get tan x minus, I'm going to get 1 because I'm going to get tan x to the 0 power, which is just going to give me 1 dx. I'm going to distribute that minus. So this is going to become a minus. This is going to be a plus because I have a double negative here. And now I can integrate this. I have the integral of 1 is x, and then I have my plus c. So there are times that you can apply the reduction formula more than once until you get it down into a form that you can integrate easily.